Hello everyone, my name is Pan. I'll be presenting my AP Physics project. The topic is rotational motion, and the question will be about rotational kinematics with a projectile motion. So my scenario says a ball is thrown into the air at an angle of 50 degrees to the horizontal with a velocity of 12 meters per second. As the ball leaves the pitcher's hand, it has an angular velocity of 4.5 radians per second. How many revolutions does the ball make it before it returns to the same level? Note that the x, y, and rotational motions are all completely independent, and the linear velocity given is not the velocity in the equation v equal omega r. First, we'll be starting by drawing a diagram, as you can see in the picture on the left. Next, we will be finding the initial horizontal velocity. We get velocity 12 meters per second times the cos of angle 50. We'll get about 7.713. There is no horizontal gravitational force, so the delta x will be equal to 0. Then in vertical velocity, we get 12 meters per second times the sine 50, so we'll get about 9.193. There is a gravitational force with 9.81 meters per second square, but delta y will remain 0. Then in the rotations, it's given that the angular velocity is 4.5 radians per second, so the omega is 45 radians per second and the angular acceleration is equal to 0. Delta y will be equal to 0 since the ball returns to the same height, and as the ball is in the air, there is no force to make it change its rotation, so the angular acceleration is equal to 0. The formula we will be getting from delta y is delta y equal vyt plus half gt squared, and since delta y is 0, this equation will be reduced to t equals 2vy over g is equal to 0.9371 seconds. Omega can be found by using omega t plus half alpha t squared equal 45 times 0.9371 equal 42.1695 radians. Converting from radians to revolution, we know that 1 revolution is equal to 2 pi radians. So if we have 42.1695 radians divided by 2 pi, is equal to 6.71 revolutions, so the ball rotates 6.71 times. In the following question, if the angle of the ball thrown changes, will there be any change in the answer? The answer is yes. There will be changes as the angle increases. Horizontal velocity will decrease and vertical velocity will increase.
Next, what is the mass of the ball if the momentum is 16.24 kilograms time meter per second? Using the momentum formula, P equal mv. So we'll derive the equation to solve for mass, so we get m equal p over v. And the momentum 16.24 divided by the velocity from the scenario 12 is equal to 1.353.
So the next question. What is the linear speed of a point 0.1 meters from the center of the ball? So this picture is the picture of the ball with a point 0.1 meters from the center. We need to derive the equation S equal R data to V equal R omega. So first we get ds over dt equal R d data over dt, and the V is equal to ds over dt, and R d data over dt is equal to R omega. So that's how we get the equation V equal R omega. Then we put the number in 0.1 meters times 6.71 radians per second. We get the linear speed of 0.671 meters per second. Next, if the radius of the original ball is 2 and the imaginary ball is 4, what is the derivations of the equation? With the tangential velocity, it changed from 2 to 4, so v1 is equal to v2, and then we change it to r1 times omega 1 equal to r2 times omega 2, and the r1 is 2 and the r2 is 4. So we put in the number, then we'll get omega 2 is equal to 1 over 2 times omega 1. Next is the argumentation. The mass of the ball has increased from the original. Marx says that if the mass increases, the revolution of the ball will also increase. However, Jean argued that if the mass increases, then the ball will also drop faster, so the revolution is lesser. Question A. Does Marx's reason correct? Justify your answer. Marx's reason is correct about the increases of revolution of the ball because the ball with the greater mass will roll further. Question B. Does Jean's reason correct? Justify your answer. Jean's reason is incorrect because the ball will not drop faster but will roll further. That's the end of my presentation. Thank you.